I'm Jane Burston. I'm the head of the Centre for Carbon Measurement at the National Physical Laboratory, and I'll explain, as Phil said, a little bit about the centre, but also about the National Physical Laboratory as context for Tom's talk on the technical aspects around CCS. So what is the National Physical Laboratory? Well, we're a world-leading science and technology lab, and we're one of the top 3 national measurement institutes in the world, alongside NIST in the US and PTB in Germany. And there's about 650 staff here, most of whom are scientists, an additional 200 co-workers who are secondees from industry, academia and other national measurement institutes around the world. We work very closely with industry, and that's because we're focused on science with impact. We need to make sure that our priorities are aligned with those of industry, and also that we are delivering demonstrable benefit to the UK and the UK's quality of life. So you might think that's why, quality of life, that's why there's a pint of beer up here. Well, not quite. The pint of beer is there because back in 1215, the Magna Carta established measurement for the first time. And the reason was people wanted to know how much beer they were getting. So nice to see our ancestors had the same priorities as us. So how does this apply to today? Well, NPL develops and disseminates the UK's measurement standards and ensures that they're part of a network of national measurement institutes around the world, applying those standards consistently internationally. We help provide R&D for the public and private sector and knowledge transfer between industry and academia and government. At the beginning of this year, we established the Centre for Carbon Measurement at the National Physical Laboratory. And our role here is to support industry in the measurements needed to accelerate the low-carbon economy. So we're working in this area with utilities, but also with small companies, instrument manufacturers, to help develop the sort of technology that will get CCS at commercial scale. The centre covers a range of different activity, and I'll go through those very quickly in a second. But our stakeholder advisory forum includes all of the stakeholders that we've got from government through to academia through to industry. And on that body there's DEC and the Department for Business, Innovation and Skills, which owns the whole laboratory. So the 3 areas that we work on before I hand over to Tom, the first one is climate data. And what we're doing here is providing confidence in the measurements that are taken about the Earth, primarily from satellites. We provide quality assurance of the data that's coming back from satellites and calibration of the instrumentation that's used to take the measurements. Secondly, carbon markets and accounting, and this is where a lot of the work that we're doing on CCS falls under. If the climate data area is helping government and international governments to create legislation and regulation around emissions, then carbon markets and accounting is about helping put those regulations in place. So the environmental monitoring team, of which Tom is a member, it's about 30 scientists working on emissions measurements, physical emissions measurements for the EU emissions trading scheme using differential absorption, LiDAR, and a number of different techniques. And we also support government departments like DEFRA to create international emissions factors. So, for example, we're working on the emissions factor for methane at the moment, methane emissions from livestock. And finally, low-carbon technologies. And this is about helping to both develop the technology and then provide the performance assessments that are required for businesses to get investment, either government funding or private investment, and to get custom. So this is across all of the range of technologies, from fuel cells to renewables to instrumentation to measure or detect and quantify leaks in carbon capture and storage. So I will now hand over to Tom for more detail about the environmental measurements team and CCS.
Okay, thank you, Jane, and thank you all for your attention this morning and inviting me to talk today. I thought I'd just continue the background with just a little bit of description of the environmental measurement group, the group that I'm a part of. We've got a 25-year history at NPL of making environmental measurements. and as you said, about 30 people working in the group, and about half of those are actually working out in the field, making directly environmental measurements of various different parameters, from gas measurements, aerosol measurements, increasingly some biotech, bioaerosols and things like that. We work across a wide range of different activities, from the research and instrumentation development at the more fundamental level, and then actually exploiting those measurement techniques in measurement services. And obviously a key part of what the National Physical Laboratory's role is the calibration and validation of different techniques, ensuring that the techniques that are used within the environmental field are actually fit for purpose and are delivering the measurements that are needed by the customer. And obviously linked to that, there's various consultancy, protocol development, development of international standards, and feeding into environmental legislation. And this work is done across quite a wide client sector range, a lot of work for industrial customers. We also work quite closely with a number of academic groups on that fundamental research. And then that work feeds through into regulation and work for central and local government. And underpinning all of this actual exploitation of environmental measurements, we have research into the measurement techniques and standards supported by the National Measurement System. So moving actually on to the focus of today's talk, looking at CO2 emissions from the CCS process. As we've already heard, and no doubt we'll hear throughout the day, obviously in each step in the process we need to look at the losses in the process and the efficiency of each step. And from NPL's point of view anyway, we would say that direct measurement is often the best way to do this, or at least to validate other techniques. And also any monitoring requirements are obviously crucially important, both the safety issues we've heard and this public reassurance need that is crucial for the successful uptake of CCS. And it's not just a matter of having a nice technology that's had lots of investment in it. You also need to demonstrate that it does meet the requirements of the system. So validation of the different measure techniques is absolutely key to the uptake of the different methods, and particularly when you've got innovative technologies coming through, demonstrate that they actually meet the requirements. And what I'm going to talk about today is some of the principally optical techniques that we're working on at the moment, and I'll briefly also mention some of the acoustic technologies, some of the acoustic capabilities that are also within NPL, they're not in my particular group. And as we've said, there obviously are many stages in the CCS process, and there are opportunities, potential emission sources throughout that stage, both in controlled emissions and in fugitive leak and so on. So I'm going to focus on my particular area of expertise, which is on the optical measurement technologies. And the key thing about CO2 from the optical point of view is that it absorbs infrared light. That's why it's a greenhouse gas. That's why we're worrying about it on the global scale. And if we look at the spectrum of CO2 across the infrared region, as we have there, you can see that it absorbs in different bands, and we can target those specific bands for different optical measurement techniques depending on the method we want to use and the measurement scenario we want to address. And so we can also have different optical configurations to address different measurement applications. And the four different configurations that I'm just going to quickly talk through are the simple sort of the in situ sensor, where you're actually just making the measurement at the point. Then this open path system, where you're constructing a defined path along which you make the measurement. And then some of the more potentially interesting systems about remote sensing, where you actually are making a measurement from a point of a much wider area. And we're going to talk about some both passive and active remote sensing capabilities and techniques. So if we just say very little bit about in situ sensing, obviously primary use for these is continuous long-term monitoring of either the process streams or emission sources, and obviously widely used within industry generally as the continuous emission monitors, which are providing the regulatory monitoring of controlled emission sources. So these are basically instruments placed in stacks to provide the long-term measurement of the emission from those stacks. And what the work that we're working on at NPL within the CCS area is supporting the development of CEM type instrumentation by other instrument companies, but by developing the validation and the test facilities that are needed to assist in that development process and demonstrate the appropriate use of those measurement techniques. And also work is going on internally on looking at analytical methods that are suitable for purity analysis in CO2 streams, so looking for some of the breakthrough products and potential risk-causing impurities that might be present in the streams, and what sort of technologies may be appropriate for that. And a wide range of different systems are currently being investigated. But if we move on to the open path sensing systems, this is basically where you can define a path in the atmosphere that you want to know the CO2 concentration over, and these can be used to make very, very high sensitivity measurements of CO2 over many hundreds of meters up to kilometre path lengths. The technology that we're working on, and it is one of a number of technologies, is Tunable Diode Laser Absorption Spectroscopy. And this type of system effectively uses the same type of very small semiconductor lasers that are widely used throughout the telecom industry. This means they're very low power systems, so you can end up with very small and flexible pieces of equipment. But you also have a very precise beam of light that you can control very well, and you can also control the wavelength of these lasers very tightly, so you can very specifically target CO2 as your measurement gas. So basically what you're doing with the system is you have a source at one end and then a system of reflectors or mirrors directing the beam wherever you want to make your measurements, often ending in a cube corner away to reflect the light straight back to you. Now, so this type of technique is very suitable to either fence line monitoring around your installation, or you can bracket a particularly sensitive area if you know you have an injection wellhead or a part of the process plant that you are concerned or you want to have particular focus on. You can bracket that by putting your beam of light around the system. So similarly, this type of technology is also used in safety applications where you're looking for early warning of a leak because of the sort of sensitivity that this type of measurement technology can provide for you. However, there are a couple of limitations to the technique that you need to be very aware of in the application of using it. One, of course, is it can only be made over a defined, a fixed path. So basically, where you direct your beam of light, where you can put your mirrors, that limits you to the areas that you can actually measure over. The other issue you have to be aware of, which is the case for most optical measurement techniques, is that what you're measuring is the average concentration between your source and your final reflecting mirror. So you're measuring the average concentration along your total path. Now what this means is that you can't actually discriminate between a broad plume of low concentration that's spread out across the entire path or a very high concentration localized plume that might be occurring at one point. So again, you have to be aware of this limitation in terms of designing the paths you have and also in the response that you're going to make to an elevated concentration. And all of that needs to be taken into account when you're designing both the system itself and the application that you're using it for. In terms of the actual measurements that we're looking at for CO2 emissions with this type of technology, what we're aiming for is a very challenging technical objective to measure a change of around 1 part per million of CO2 in the path, and that compares to the atmospheric background of typically sort of 380 parts per million. So you're looking for about a 0.3% change in that average path, and that with path lengths of up to around 1 kilometre. Now, the level of precision that requires for the measurement is a very significant measurement challenge. One of the principal issues you have there is how do you tell the difference between a change in the CO2 level and the variation in just the atmospheric system itself, so a temperature variation along the path, a pressure variation along the path, or indeed a humidity variation along the path. all of which can easily be at that sort of level. And so you need some way to discriminate between these different competing effects to the overall measurement. Now, the way that we are looking at this system is to try and address the atmospheric density variability by looking at a stable component of the atmosphere. In this case, oxygen is an ideal component for this. And this type of compensation is being used in a number of different systems, including some of the future satellite technologies using the same sort of oxygen compensation mechanism. And basically by making a simultaneous measurement of CO2 and oxygen, and you can pick out the atmospheric variability through the oxygen measurement and ratio that out. Similarly, but if you've got very good knowledge of the spectroscopic behavior of the system, you can also make simultaneous measurements of CO2 and water vapor with the same system. So you can actually have an online measurement simultaneously providing CO2, oxygen and water vapor. And so if you're seeing humidity variations along the path, you can also cancel that out. What all of this means is that you are requiring to make that measurement at the level of, as you say, about 0.3%, and the sort of levels you're then trying to compensate for, that's a temperature change of less than 1 degree, and it's a pressure change of less than 300 pascals. So that, knowing that variation drives your requirement for both the sensitivity of the CO2 measurement and the sensitivity of the oxygen measurement. And also, you can, by looking at the high-resolution spectroscopy, looking at real detail of the signals you're getting back through the system, you can also get other information about the source of variability. And this particular model shows what you're seeing for small temperature and pressure changes and how that affects the line that you're actually measuring with this particular measurement technique. And so you can see very clearly that there are spectral differences in the cause of the change, which you can also use to back out the information and just leave you with the underlying variability in the CO2, having eliminated the other possible sources. Moving on to sort of the next technology area that we're looking at, this is passive remote sensing. This presents this very attractive option for screening plant areas or sensitive areas for unexpected emission sources. So it's this first level of sensing, this screening to make sure if you've got an issue occurring or not, that can then trigger further measurement requirements. And the usual method for this with any gas that absorbs in the infrared spectral region is that we can use basically a thermal imaging camera, so like one of those sort of security camera systems, but you can then spectrally filter to one of those absorption bands in the spectrum of CO2 that we saw earlier. So you can target the absorption band of a particular gas and basically form a 2D live image of the scene, with the gas appearing as a dark cloud within that scene if you have a leak occurring. Now, this sort of technique is already widely used within the petrochemical industry for screening tanks and process areas for fugitive volatile organic compounds. But the issue of moving to CO2, there are a number of issues that come with that. So this type of method is very good for making a rapid qualitative assessment of sources and screening for fugitive emission sources. It's generally very easy to deploy, but it's much harder to make quantitative emission measurements with this type of system. And so you need it basically as this first screening tool that then leads on to the next level of monitoring. But in terms of the CO2 measurements, making it with this type of measurement, then you know that you have certain detector materials available that operate in different spectral regions. And given where we know CO2 absorbs, this indium antimonide provides the best detector material for that, operating in between 2.5 and 5 microns. And again, if we take an example requirement of looking for a small 1 meter wide plume containing 1% CO2 as sort of the detection limit we're looking for, we can use that to define the technical specifications we need for the camera and for the selectivity that we need for the CO2 measurements. And again, we have to address this issue that although we're looking for a small plume, we're going to look for this over a wide area at a long distance, And so we have to allow for the fact of with the path averaging effect we're going to get with the system. And so again, we can follow that through to define the percentage change that we're looking for across the path. And in this case, it's about 100 ppm we'd be looking for over a 100-metre path. And in order to achieve this, we need to spectrally filter to target the CO2, but we also need to thermally stabilise that filter and cool it so that we can eliminate background effects from the filter and just be looking for the change in the CO2 level rather than variation in the filter itself. And those types of processes, we're currently doing laboratory testing of this system at the moment, and we'll be taking it out into the field within the next couple of months. So the final optical technology I wanted to talk about, actually was mentioned earlier, is the LiDAR system. So the system we have is a differential absorption LiDAR, and this basically acts as an optical radar system. We're firing a pulse of laser light into the atmosphere, and we're looking for scatter back from particulates and aerosols in the atmosphere back to the source. Now, what we can do with differential absorption LiDAR is we basically transmit two beams of light into the atmosphere, one of which is targeted on the gas that we're interested in, and one of which is at a nearby wavelength which can act as a reference. And so we can basically ratio those two signals that we get back, eliminate all the effects from the aerosols and the scattering, which is a very complex process, but just leave ourselves with the absorption of the gas that we've targeted on. And effectively what this gives us is the ability to, from one point, make a 3D map of the concentration in the atmosphere from a remote system. And we're typically talking here about ranges of up to a kilometre from one point, and we can get spatial resolution down to a few metres. And the system we have has both infrared and UV, so infrared and ultraviolet capabilities, and we're able to target a wide range of species with measurement sensitivities down to levels of 50 parts per billion. So it can be a very sensitive technique. As you can see, it's not the smallest or cheapest technique in the world, but it does provide you with a unique capability to map these profiles. And we've done a lot of work looking at greenhouse gas emissions, principally methane, but also VOC measurements in the petrochemical industry. But we are making experimental testing of CO2 measurement performance at the moment. We've just come back from our first field campaign from that, and we'll be reporting on the results of that very shortly. So CO2 measurements with this type of technology is feasible. Calibration is obviously key to this, and we have numerous sets of different capabilities for validating both gas sensing and optical sensing instruments. And a key feature here is actually being able to test those instruments in the conditions they're used in, not just in a nice laboratory controlled conditions, but actually to expose them to the type of systems that they're going to experience when they're used in the field. So saying validation is crucial to the work that NPL does, and supporting the testing of validation of new instrumentation that's coming along from other instrument developers. Final thing I wanted to mention a little about was just the acoustic capabilities within NPL. There aren't specific activities at the moment focused on CCS in the same way as on the optical side, but there is a wide set of capabilities here, and we're very keen to see how that might fit into future CCS monitoring requirements. The main issue here, this is just as we've discussed, some of the possible needs for subsea CO2 detection, and some of the possible acoustic solutions that might be some of the new technologies that possibly can address some of the issues that we've heard mentioned earlier. And so very keen to hear from you about whether you've had experience with these types of technologies, and also talking about the measurement requirements and how acoustic systems may meet those requirements. So, just to conclude, NPL has recently launched the Centre for Carbon Measurement, addressing these various issues for climate data, carbon trading, and low carbon technologies. We know that fair and consistent measurement of emissions from the CCS process are going to be crucial for the future uptake of the technology, and that accurate quantification is going to be important for successfully inclusion in emission trading schemes. And we know that there are a number of measurement capabilities. What I've just given you a flavour for is very much a subset of the total systems that are out there. What we at NPL are keen to help you with is both meeting the needs for the measurements, but also where you have technologies is this validation and calibration of those technologies to assist in the development of new measurement techniques. And so this developing fit-for-purpose measurement capabilities is going to be crucial, we believe, for the future success of CCS. So, thank you for your attention.